Hello everyone, welcome to another video in the Raspberry Pi 4 bare metal assembly programming tutorial series. So today is the day we are actually going to blink an LED on and off. So we've been building up to this point, and each video has tried to explain things in a step-by-step way so that if you are jumping in and you've never done this type of thing before, it might sound like I'm speaking basically ancient Egyptian or a language you don't know with lots of jargon. And I guess the solution I got for you is watch the previous videos. In the last video, we also talked about which resistors and how to orient an LED so that you don't burn anything out and so that everything works for you. So if you haven't dealt with that before, that video explains why we're doing the things that we're doing. And I guess that's all I really got for you. Let's jump into it. So what is the GPIO? Well, the GPIO is the general purpose input-output pins. So when you look at the Raspberry Pi, this is an image I found on SparkFun, you can see that there's 3.3 volt pins. These are always at 3.3 volts. These ones at 5 volts are always at 5 volts. The ground pins are always at ground. And then some of these pins say GPIO on them. And these are the pins that we're actually going to be controlling. Now this video, to try to keep it short and to not go overboard and make it hours and hours and hours long, we're going to be doing some hard coding. Now we'll fix that hard coding in future videos, but if we can hard code a value and make it run, then I'm gonna call that a win, and in a future video we can generalize it and make it more user-friendly for switching pins. But in this video what we're going to do is control GPIO 21. We're going to make it so that it is an output pin, not an input. It'll be input by default. We'll switch it to output, and then what we will do is we will turn it on and turn it off. That is what will turn our LED on and off, and we will be using this ground pin for the circuit to run through. All right, perfect. So if you look at the code, I've added some comments in here, and we will be using some of these manuals today. Specifically this one here, this BCM 2711, we will be using that quite a bit. But first, let's do a very short recap. 64-bit, we're using a V8 processor, and starting address is hexadecimal 80,000. After that, we are going to run through this cycle that we talked about in a previous video, where we determine what the core ID is, and if it's core ID 0, we jump down to running. Actually, I want to call running main because I like that better. All right, so this is where we're going to be writing our code today. Now, the first thing that we need to look at is actually this manual. Now, you'll notice that this is the peripheral manual for BCM 2711. Why do we need this manual? Well, if we look at the Raspberry Pi 4 specifications, it says it is a BCM 2711. So Raspberry Pi 4 tech specs, BCM 2711. So that is why we are using this manual right here. Now, the very first thing that we need to do is we need to define a base address that we want to work with. And I will put this right up here in kind of a no man's land. We'll call it GPIO base. And the base address is FE200,000. Where does this number come from, you may be asking? Well, let's take a look. So if we go over to page 65, you can see that this is the section dealing with general purpose I/O, the GPIO. And it describes some of the things that there's 58 different lines that we can work with, and there's a lovely picture here that we're not going to decipher. But if we come here, you can see that these are the registers that we will be working with. They're assumed to be 32-bit. And now you might be wondering, okay, so registers, those we've talked about W0 through and it just goes up and up and up, and X0 up and up. So we'll be dealing with X's and W's, and yes, we will, but that's not the type of register it's actually talking about. So what we're using is something called memory mapped I/O. In the past, I've described RAM kind of like a gym locker, or a locker bank, I should say, with multiple lockers, starting with 1 all the way up to maybe 100, depending on the size of your gym. Whatever you put in the locker, in this case, we put a byte in our locker, and it's there for us to take out of memory later on. So we can put things in, take things out. With memory mapped I/O, it's not a normal locker. It's more like a post office box or a drop box. We put the number in there and it goes somewhere else. So if you ever see like those old spy movies where they put something in a locker and there's someone behind the locker, they had cut out the back and they take whatever was in and they take it out. And usually it's like for nefarious reasons on the mystery shows and things like that. Anyway, that's kind of what's happening here. We're going to store a number into an address, and it's going to go over to the peripheral chip, and it's going to do stuff for us. So it's kind of a clever way of doing it. I think there's historical reasons why we do it this way, but anyway, let's get into it. We can see that each one of these is going to be 32-bit, and the RAM address, it says, is 7E200,000. Now, those of you that are very astute may notice that this is not the number 7, it's an F. Why are we doing that? So let's take a look. If we switch over to page 6 in the manual, you can see that it says a peripheral described in the document at the legacy address of 7E, in this case 7E200,000, is actually visible to the ARM at FE, in our case FE200,000. So that is where that number comes from. So there's a few things we will actually be working with. We'll be working with the GP function select, GPFSEL. There's 0 through 5. You'll notice that these work off of offsets. So offset 0, 4, 8. This is 10 in decimal. This is 16 in decimal. But you'll notice that it's 4, 8C, 0, 4. Where's the 8? If you look at the Raspberry Pi 3 manual, you'll notice that 1.8 says the word reserved. So I'm imagining if we ever need a GPFSEL 6, they already have a spot prepared for it. Very clever of them. Anyway, let's start talking about the GPFSEL 0. It is the function selection. So if we go here, we can see that this is for setting GPIO 0 through 9. The next register will deal with 10 through 19, and the next one will do 20 through 29. So the one we care about is this one, because again, we'll be working with pin 21. And 21 is right there. Now, let's first look at its offset. Its offset is 8. So let's just put in here GPFSEL2 equals 8. We will need that for our code soon. And when we look at it, each mode is comprised of 3 bits. So there's all zeros, or the number 0, it's an input, and they're going to be inputs by default. If you set it to 1, it will become an output, and then there's these 5 alternate functions for doing special purpose things, as we can kind of see here in the parentheses. And we won't be doing anything special purpose, we'll just do regular GPIO. All right, some people are more visual, and I think explaining this visually might be helpful for all of us. So let's explain it visually. Now, we know we'll be working with 32 bits. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2. So that's 32 bits that we have there. If we break it into groups of 3, the way that this will work for GPFSEL2 is like this. So if we want to work with pin or GPIO 20, we would set a 1 here if we wanted to make it an offset. But we want to set GPIO 21 to be an offset, so we will want a 1 there. So let's start writing our code. I think it'll make sense once we start looking at code. We're going to move into X0 our GPIO base. And then after that, we are going to move into W1, because remember, these are 32-bit. So we want to use W's, not X's in this case. We'll have the number 1, and what we'll do is run left shift, and we will want to shift this 3 places. So what we're doing here is we're moving 1 basically here, and then we're saying, oh, we actually want to shift you 1, 2, 3 to the left. So let's look at this LSL real quick. This is a new instruction that I don't believe we have dealt with before. So it's always helpful to see where this is in the manual if you wanted to do more reading. So when we look at LSL, we can see that we have a destination register, and we have where we're starting from, and then our shift. It allows us to shift through the entire range, whether it's 32-bit or 64-bit. I did try to make this video before, and I actually used move Z in that video. And move Z allows you to store like the 1 and shift it right away, but there are only certain values that you can shift. And for some reason, the number 3 actually did work, but then when trying to work with other pins, it was not working at all the way that I anticipated, because I did not read the documentation well enough. So it's always good to read the documentation. All right, let's go back to LSL. This allows us to shift it over. So again, the way this is working is the 1 is starting over here, and then we're shifting it 1, 2, 3 bits over. Now you might be wondering, great, all right, we have that. How do we actually make it do anything? And the way we make it do something is by using the STR instruction. And what we'll do is we will store it at the base address with an offset of 8. And you might be wondering, why didn't we just put the 8 here to start out with? And I will show you that. Let's do a terminal and phasm-arm boot.s kernel8.img. Value cannot be encoded. But if we make this a 0, value can be encoded, and it succeeds. So why is that? Well, there's a clever mechanism that they use for encoding addresses in this ARM64, this AArch64 architecture that we're working with. And generally what they do, or basically what they do, is they will take 2 bytes and then they will include a shift. So if this number was a lot bigger, they would start out with these 2 bytes, and then they would shift it over however many that they want to do. In our case, what they'll be doing is that 200,000? That is not 200,000. That is 200,000. There we go. So what they'll actually be doing is taking these 2 bytes and they will shift it over 2 bytes. And that's how this number is encoded in the actual instruction itself. And what that allows them to do is all the instructions are 4 bytes long. So it allows them to encode 64-bit addresses in 4 bytes. So 8 bytes within 4. Pretty clever mechanism, but it does have those issues when you try to use really special, unique numbers. It will yell at you and say it cannot encode the value. So if you get that error, that's what that error means. So what we're doing essentially is we're going to start with this number, and then we're going to add the number 8 to it and store it into there. Now you'll remember up here we used MRS, and it took whatever this value was and it put it in the register. This one works the opposite, where it starts here and it goes into the memory address we're working with. And you can find that in the manual in a little bit of a different area. So it's not under the general instructions, it'll be under the data transfer instructions. And if you go under STR, you can see that we are taking this value and storing it into an address. And if you want to read more about it, now you know where to look. Very cool. So what we have done now is we have taken this, we've created this number, and then we have stored it in the proper spot so that GPIO 21 is now an output. So let's make a blink routine. And you can see it's going to be an infinite while loop, so as long as there's power, the light will blink. Now what we're going to do is we want to create yet another number to work with. And the reason for that is we're going to be working with GPSET. So let's find out what number we need to create. So when we look at, there's a set 0 and a set 1. And if you read about it, you can see that it only works if it's set to be an output pin. And you can see if the pin is used as input, which is the default, it's not going to do anything. But if it's an output pin, then it'll start actually working the way that we want. Now we've already done it. That's the last thing we did, was set it as an output. And the way this works is if we were to draw out the little picture again. So if we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2. That's funny. If we wanted to make GPIO 0, if we wanted to turn it on, we would set a 1 here. Now, if we want to do GPIO 21 as a turn it on, we'd have to move that over 21 times to whatever spot it would be. Now, instead of doing it the way we did here, where we would take a 1 and shift it 21, let's see if this one we can encode all in one instruction. So if we let's see here. Okay, yeah, that is large enough. And get on Google page here. So if we did the number 1 followed by 21 zeros, is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 to hex. We get this number. And okay, on my notes I'm confirming, and yes, that is the same number that we want to see. Now, we could have derived this number ourselves if we don't want to hop on Google every time we want to convert hex. And I suppose I should probably talk about that. So if we separate the nibbles, it's 4, 8, 12, 16, 20, 21. We know that this would be the equivalent in hex as a 0. So obviously it takes 2 nibbles to get this wrong. An entire nibble. There's 2 nibbles in a byte. There we go. So each hexadecimal digit can be represented by a nibble. And then this would be the number 2 in this nibble. And this gives us a 2 with 2 zeros and then 3 more zeros. So a total of 5 zeros. And if we go back to that page here, we can see that we have a 2 with 5 zeros after it. So we're able to convert between binary and hexadecimal. We've talked about this before. But anyway, that's where that number comes from. Long story short, let's move into W1 because we're done working with W1, so we can work with it again. Let's move into that, the value 1, 2, 3, 4, 5. We're going to move that value directly into there. Now what we need to do is know where to store it. So back to the documentation. So GPSET 0 is at 1C. Now you may be wondering, what if we go past bit 31? Because starting at 0, there's 32 bits total, which means 0 through 31. Well, that would mean that GPIO 32 would be the 0th spot in GPSET 1. So hopefully that makes sense. I mean, this does pins 0 through 31, or GPIO 0 through 31, and then this one will do 32 through 57. If we, up here, 32 through 57. This is the set. The next one we actually will work with, though, is the clear. So the way clear works is the same way as set, except one will clear the pin instead of setting it. So we can actually duplicate our logic. So we will need to know GPSET 0 and GPCLR 0. And set 0 was 1C, and clear 0 is 28. So let's put in here GPSET 0 is going to be 1C, and GPCLR 0 is going to be at 28. And confirm that in my notes. Yeah. Don't want to lead you astray. So this is basically identical to what we did before, except that the offset we'll use is this one. So this will turn the pin on, and this will turn the pin off. Now we want a delay, though. We don't want it to be turning on and off so quickly that the light is just basically dimmer than it would be if it was on all the time. We want it to actually turn off completely and then turn on and turn off and turn on. So we need to create a delay. And again, we're going to be hard coding this. We're going to move a large number into x2 because we have not been working with x2 or w2, and we don't want to break especially x0 because we are using it here and we're not resetting it every single time. The number we will use is, let's see, I have 1, 2, 3, 4, 5, 6 in my notes here. This number, you might be thinking, how can it be stored using that methodology we talked about before? This number is stored cleverly as well. It actually will start with one larger than this and subtract one. It's stuff that the assembler deals with, and honestly, in some ways, I don't know, I think the best way of doing it is confirming through the compilation process that when you run it, it doesn't fail on you. I don't know. It's something you'll just have to get used to. The fact that it some numbers can be encoded and some can't. All right, so we are going to use the subtraction command, and we're just going to subtract 1 off of it. And then we're going to do the not 0 version. So up here, we did the 0 version, compare branch 0. This one's going to be compare branch not 0. We will look at x2 and call delay loop. So this one will be a little bit different though than anything we've dealt with previously. Previously we branched and we get back to where we want. We don't necessarily have a return like a void function in C or anything like that. So we actually want to return. So subtraction works the way that you would imagine. I should start with the higher up things first. So if you go into the manual here, oh, I closed it. Go into the manual here. If you look up subtraction, you can see that you can put in where you want to store it, what you're starting with, an immediate value, and then you can even do shifting. We're not going to be doing any shifting. We're just going to work with the number 1. And the way this loop works is we start with this large number, we subtract 1 from it, we check to see if it's 0. If it's not 0, we run it again and subtract another 1. And obviously it takes time for the processor to do this, although it is quite quick. And then once it does hit 0, we're going to do RET for return. So we can't actually do a regular branch. We need to do BL instead for start delay. And we might as well look that up because we have the manual open. The way BL works is that it will go to a label, essentially, and it will take the program counter and it will save it. So essentially what will happen is it will keep track that it was at this point in the program. It will save it. It will add 4 to it. So it's getting ready for this next line when it returns. But anyway, it will go to this location, do all the code, and when it hits return, it says, what was that number I saved? And that number it saved is at this location, so it will carry on. And we will want to run a start delay here as well. And that is it. we now have the ability to blink GPIO 21 on and off and on and off and on and off to our heart's content. So let's jump to the real world and see this working. So we have made it over to real life. So let's look at our setup here. We have the leads connected in the very bottom of the header, and this is where ground is located, and then also the GPIO 21, according to the diagram we looked at earlier today. And I guess red in this case is hot. GPIO will provide positive 3.3 volts to our circuit, and ground in this case I guess is brown. Dirt is brown, so I guess that's what we're going for. This is not official colors by any means. GPIO 21 is hooked up to the positive in the breadboard here, so that provide our positive. Ground is hooked up to negative. And when we look at our circuit here, we also we talk about this in another video. We explain why the resistor is where it is and how the LED is set up. And if you want to know more about that, you can watch that other video that came out before this one. So I guess it's time to test. Let's take out the SD card and put it into the Raspberry Pi. I make these so small. And I'll grab the power cable. We'll plug it in and start it up and see what happens. So as you can see, red and green are starting to flicker on the Raspberry Pi. That means that it's booting up. Takes a second, but there's our LED turning on and off. So we have succeeded in our goals. The next video, we're going to optimize our code so it's not hard-coded to GPIO 21. We'll use macros to do that. Hope you found this video educational and enjoyable. We look forward to seeing you in the next video.